All right. Hello again, everybody. Today we're going to do a little bit of lecture on our 104 class, and we're going to cover a little bit about anti-reflective. I had some really cool videos about how vapor deposition and how anti-reflective coatings were applied in thin films, and apparently YouTube yanked them off for copyright issues. I had stolen them from Essilor. So there aren't as cool animation to show you what it's like, but I do recommend that you go to an office a lab, whether it's an Essilor lab, a Hoya lab. Heck, we have the rep from Cherry Optical in our class in the second year, and each of them have anti-reflective uh, coating application processes. And one of the things that's interesting, and this as opticians, I think you guys or eye care providers of any kind really need to know that there's a difference. An AR is not an AR is not an AR. You have cars, and you could have an Audi A8 brand new off the lot, and you could have a Yugo from the 80s that was through Hurricane Katrina, and you taped it all up and repainted it, and they're both cars. They both have steering wheels. They both can get you from point A to point B, but there are difference in features, there's difference in quality, there's difference in how long they're going to last on the road. And it's interesting because when you're dealing with things like online or different types, when somebody says, I have a high index with an anti-reflective coating in, say, a progressive, you guys have covered a lot about different progressives and freeforms and IoT versus Hoya versus an old-fashioned fixed corridor, hard design. There's lots of different things that make up a pair of glasses, and the more you know about how things are made, like a custom-made IoT progressive or Hoya progressive or Verilux X that's custom made for someone is going to be a far different animal than what we had back in the 80s or 90s with some really rough old technology. And the old ones were still progressives, but they're not really in the same category. Well, the same could be said for anti-reflective coatings, and knowing what they are, knowing how they're applied, knowing the differences between a good one and a bad one really may make the difference between you knowing your stuff and being able to explain why what you may be carrying or selling in your particular office may actually be superior. I actually I used to do glasses for my mom, and we had a product, and I don't like to name drop, but just to give you an idea, it was a super high vision, essentially an EX3 from a company named Hoya. I used to do my mom's glasses with little drill mounts, and 2-3 years later, you look and the things were just spotless. There's no minimal scratching. They're indestructible in terms of how the coating was applied, how durable it was, how effective it was. My mom, when I moved out of state to Chicago, she ended up getting a pair of glasses through another outlet. And it was a really inexpensive pair. And it was interesting because when she got the pair of glasses, interestingly enough, what she paid for it through the retail establishment was less than what I paid for my wholesale cost of goods for my particular brand. And I said, man, this is the beginning of the end for the eye care industry, because if they can sell it for less than at retail, for less than what I paid for it in my private practice, I said, we're in big trouble. Incidentally, 6 months later, the anti-reflective coating she had on her high index progressives with an anti-reflective coating, the anti-reflective coating wore off, came right off. It was a difference in quality. It was a difference in its application. It was a difference in how it was manufactured and the tolerances in which it was applied. And again, an anti-reflective coating slapped on a set of lenses in one company may not be the same as how things are prepared with a foundation coat, multi-layer coating, with an oleophobic. Again, there's a whole series of things that we'll go over a little bit in slight detail for thin film application and deposition of coatings. This could be a multi-chapter, multi-week course, but for what we're doing, we just want to touch on the basics. So there's some videos we have for, actually Larry McKay put out some good ones about the deposition process step by step, and there's a handful others you're welcome to look at. And also some of the how an AR may be tested from a level at the laboratory to how they hold up. And again, if you ever go to a show like a Vision Expo East, you can actually see the manufacturers that make the devices to apply anti-reflective coatings, in some range from a small little refrigerator-sized box that just throw lenses in and hit a button and you're good. Other are these massive whole systems from start to finish in terms of how you strip the lens, how you score the lens, how you pre-treat the lens, how you initially do the first coatings, and then apply the there's a difference in how they are. So I wanted to visit this today, and what we're going to do is we're going to share a little presentation based upon what a thin film actually is and what antireflectives are. So again, antireflective coatings, what are they? An antireflective is literally just an exquisitely thin film applied to a refractive surface, a lens. And again, when I say it's thin, we've been dealing with 2.2 millimeters. We've been dealing for regular pair of glasses, 3 millimeters for safety, 0.12 oftentimes for our contact lenses. Well, we're talking about nanometers, microns, unbelievably thin, microscopic atomic level actually, in terms of how thin these coatings are. And if you can imagine how difficult that is to do and do correctly and accurately and repeatedly, there's a lot of science that goes on between this. And so what it does is it's applied to the surface of the lenses to reduce or eliminate surface reflections. Now, why? Why is that a big deal? One, the more reflections you get, the less light that goes through to reach the eye. Telescopes, microscopes, binoculars, oftentimes they always have if you're into cameras right now, I'm using a Rebel T6 Canon, and the lenses, the glass lenses, the aspheric lenses made in all these cameras, all these telescopes, all these microscopes, especially high-end devices, generally have a very good anti-reflective coating. Why? Why? It's better optics. Why? It's better performance. Why? From a cosmetic standpoint, it looks better. One of my favorite games is if you look at TV stars or movies or even wait staff at a restaurant or anywhere that you're in public. You can look at people's glasses and take a look at the lens. You can tell who has an anti-reflective and who doesn't. And most people can't put their finger on it, but those with an anti-reflective, it's simply just cosmetically looks better. Now, same type of coating that they use for, like I said, telescopes, camera lenses, binoculars. Another thing that's of interest is we talk a lot about lighter and thinner lenses, higher index lenses. We've got CR39, which is a 1.498 index. Spectralite 1.5, I'm sorry, Trivex rather, I'm dating myself. 1.53 index of refraction, polycarbonate 1.586, and then we do our high indexes 1.6, 1.67, 1.7, 1.71, 1.74. And it turns out, interestingly enough, the higher the index of refraction of a lens, the more reflection it gives off. You lose more light in reflection from the front surface and the back surface of the lens that doesn't make it to the patient's eye. So not only cosmetically do you get more reflections in a high index lens that will be seen by observers, but you lose more light to the end viewer, or essentially to the patient's eye. So again, the performance is better, so less reflection with an anti-reflective. The better the anti-reflective coating, generally, the fewer reflections you'll have, the better the performance. And again, reduces reflections for better patient comfort. You get nighttime glare reduction, lights in office, reduces fatigue. I'm less interested in those personally because the nighttime glare is a big one. If you have a lens that has a lot of reflections, especially high index, as opposed to a lens with fewer reflections, it's generally just a better outcome. Now, and again, from a cosmetic standpoint, it looks better. Again, take a look at classmates, friends, family, movies, newscasters, just people in public. You can actually look and pick out, yes, you have an AR, no, you don't. And now some of the thin films that we're talking about, like blue blocking, they're not anti-reflective, but they're selective in terms of the wavelengths that they reflect and allow through transmit. So in this particular case, this is how we've talked about how light refracts rather. So if this is the normal and in a single surface interface, you've got a light ray coming at an angle. Well, if we go from air, which is an index essentially of 1, and then to any material, pick your eyeglass material of choice, it will actually refract towards the normal to an exact amount towards the normal. And this is how, and the higher the index of refraction, the more this deviates this way. Now, again, the more it refracts, the more it bends light, the more effective it is, the less you need in terms of lens material to do the same job. Now, we've talked about high index, and hopefully you've covered this in some of your earlier classes, but this is Snell's law, and if you have the index of where you're coming from, and you know this angle here, well, if you know the index you're going into, you can calculate how much it deviates that and how much it bends light. And again, the more effective a lens bends light, the less of it you need to affect change. So high index lenses use less material to bend light more effectively. So you have thinner and lighter, well, thinner lenses potentially. Now, this is how all of our lenses work in a nutshell. However, what it's not taking into account is there's some light that's reflected. And here, what's always really cool is the angle of incidence equals the angle of reflection. So if it comes in from this angle to a normal, this little dotted line that's 90 degrees, it'll leave at exactly the same. That's how mirrors work. Well, even though it's not a mirror, it's a lens, you do lose a percentage of the light to reflections. And there's a really cool formula. And again, let's ignore what was refracted. This is what we've been dealing with the whole time through optics and opticianry. Let's ignore that for a minute. And let's just deal with the reflected light. Well, it turns out there's a formula. And essentially, it's the index of refraction minus 1. So say 1.498 minus 1 divided by the index of refraction plus 1. So it would be 0.498 divided by 2.498. Take that number and do the math and then square it. And that will actually give you the percentage of light that's lost at this surface. And you don't lose it before you hit it. You don't lose it in it, but you lose it at the interface here. And it turns out if you do the math, the higher the index of refraction, n minus 1 divided by n plus 1, and then square that, gives you the percentage. And the higher the index, the more light is going to be reflected off of that surface. It's just a physics thing. So if we went through this, and I'm not going to have you guys go through potentially, maybe you will for homework, just to get the idea. But if we actually put the 1.498, if we put 1586, if we put 170, this is what it looks like. And if you're looking at CR39 with an index of 1.498, the reflection from the front surface alone, you're losing 4% of the light. Now, only 96 makes it through, and then there's more lost at the next surface, so you lose close to about 7.7%. For our purposes, let's just say you lose some from the front, some from the back, and so it's almost 8% that you lose. Only 92% goes through. Trivex, higher index of refraction, you lose a greater percentage of light from the front. Not too much more, but about 10% more. Let's go down to the high indexes. A 174 high index lens loses 7.3% of all the light is reflected away from the patient's eye, and that's just the front surface. If you did the other surface, you're looking at close to 15, it's like 12 to 15% of all the light that you're trying to have go through to that person's eye is literally being reflected, and it's more annoying. There's more distracting. It's more obvious. Cosmetically, it's worse, and optically, you're not getting as much through, and that's why many of our camera lenses and microscopes have an anti-reflective to essentially minimize reflections, improve transmission of light, and essentially hopefully get a better image and more back to the eye. And notice how the higher the index, the more you're losing through each surface. So how do we fix this? Well, it turns out that if I put a coating Let's go back a little bit. If I put a coating of a known index of refraction, it'll be different than the eyeglass material. Let's say we had polycarbonate, CR39. Well, if I put a exquisitely thin film here, it turns out that we've seen that we have light bouncing off, and now we have light bouncing off the coating, but we also have light bouncing off the lens itself. And what will happen is the relationship between the light that bounces off the coating we put on there and the relationship between that reflection and that was bounced off of the actual eyeglass lens surface, if we can control these two in an exactly specific manner, we can cancel the two out. And it's literally like really, really cool. It's like physics. So let's show you how that works. Now, in order to do this, we talked earlier in the years in previous classes about the dual nature of light, about how light worked as both particles, photons, and waves. Well, we're using the fact that light works in waves to make this work for us. So essentially, if you broke down each of these light rays, let's pick a wavelength. Let's arbitrarily pick one, and it's red. And it's going to be 720 nanometers. Well, it turns out if we know the wavelength of the light of a specific light ray coming in, I can control the thickness of this here and make sure that these two work in such a manner that they cancel each other out. So there's actually a formula that I won't ask, but it turns out that the optimum index of refraction of any coating is if you take the index of refraction of the material you're using, polycarbonate, CR39, and simply take the square root. It turns out that that's one of the best index of the index of refraction for that said coating. It's not always available. Sometimes you have to make do with what you have. But again, it's a cool little function there. And it's actually the index of refraction that you're in versus the index of refraction of the material. If you multiply them and take the square root, well, air is normally 1. So if you just take the index of a material and square root it, the square root of 1.586 would arguably give you the best index of refraction for the coating we're going to try to apply to that. But again, this is just one of those interesting things that I always call cool. Ignore the 180-degree phase shift. It's more of a physics thing. We'll just ignore that for now. But now let's isolate these two rays here, these two light rays that are coming out. And again, we're going to put them next to one another. And it turns out that, remember, they act like waves. We're going to use that to our advantage. So if you remember anything about waves, every wave has a wavelength from right here. You go down to the trough, and then up to the crest, and then back here. So this one full amount is one full wavelength. So let's just argue that it's a certain amount. Pick a number, I don't care. However, the height of this is the intensity. So if you had a very high wave, a really high crest and a low trough, this would be a more intense light ray. And it works for light, it works for sound, it works for any wave that we have. So now if I take this light wave of a certain wavelength and I add it to another one, and they're exactly what we call in phase. Notice how this trough matches this, and this crest equals this. Well, if I added these two, if there are two sound waves that were exactly in the same wave and they're exactly in phase, it actually doubles it. Same wavelength, but it becomes twice as strong. It becomes twice as high. It becomes twice as loud if it's sound, twice as bright if it's light, more energetic if you get. And this is a pretty cool function of how waves work. If you had one wave in water and another one that they were both sort of added together, they get bigger. If you had two waves, sound waves, and they're in the exact same wavelength, and you added them together and they both added up, you would actually get double the sound. Well, it's the same thing with light. If I have the same wavelength and they're lined up in phase, it makes it stronger, it makes it brighter, it makes it more, it's an additive effect. We call this constructive interference. They're interfering, this wave is interfering with this, but because they're adding together, it's constructing, it's making it bigger than it was. And this is how light works. And again, we're at a specific wavelength. We're not talking about white light, we're just saying pick a wavelength I think we started with red to begin with, say 720. So if I have a wavelength that's exactly 720 and another wavelength that's exactly 720 and they're both in phase, they'll add together and construct and make it the same wavelength, hasn't changed, but because it's a higher amplitude, it's going to be a brighter of that same wavelength. Now, if you use that logic and twist it on its head, there's also what's called destructive interference. Same wavelength, same light wave, but this one, we're going to do one where we're going to do it what's called out of phase. When this blue one goes down, this red one goes up. Well, if this is -1 from the middle of this line and this is +1, it turns out that if a -1 and a +1 is 0. If you follow this down, this 0 plus another 0 is 0. This +1 here, go straight down and do the -1. It turns out that if I can make the exact same wavelength, and if I can put it out of phase by exactly 1/2 of a wavelength, they line up just the way that you're seeing right here. And if I add them both together, it cancels out. This whole thing becomes 0. That's called destructive interference, and that's how an anti-reflective coating works. Incidentally, that's how noise canceling headphones work. Essentially, they take those wavelengths, they process them through, they try to make something exactly the same but a half of a wavelength out of phase, and it makes it so you don't hear it. You get the insulation so you don't hear it, and then the noise, you hear about active noise canceling headphones. This is what they're trying to do, only with sound waves at different frequencies. Now, how do we apply this to our lenses? Well, it turns out that if I have a wavelength of any one, we talked about 720, and it comes all the way into here and it hits the reflecting off of the coating, you're going to get something of this wavelength. And then as it goes through the coating itself and hits the lens, it's going to come back. And if I can make the reflection off of this coating and the reflection off of this lens to match up so that they're exactly out of phase by 1/2 a wavelength, it's going to make it so that it absolutely disappears. So these two yellow will cancel out entirely and you simply don't see them any longer. Now, without getting into too much detail, and I don't think that that's appropriate here, but it turns out that, remember, light slows down in a refractive medium. The wavelength in air is a specific. It actually slows down and the wavelength becomes shorter based on the index of refraction. So I could ask you, what's the wavelength of a 720 nanometer wavelength? If it's in CR39, well, you just take that 720 and divide it by the index of refraction, and that will give us the length of the wavelength of that 720, and it'll be a little shorter in here. Now, it turns out that if I can calculate what the wavelength is in the medium, and I can divide it by 4, what that does is I get a 1/4 of a wavelength down, a 1/4 of a wavelength back, and when it comes out, I'm actually going to be 1/2 of a wavelength out of phase, so that these two line up and they cancel each other out. That is an anti-reflective coating in a nutshell. If I have the right size coating, thickness coating, if I have the right index of refraction coating, if the light rays bouncing off the coating and the light rays bouncing off the lens cancel each other out, I don't have a reflection anymore. It's borderline brilliant in its simplicity, and it's the coolest thing ever. We have a problem though, and that is we talked about this particular wavelength, 720. Well, that's great, but if you have all the colors of the electromagnetic spectrum that are in the visible spectrum, red, orange, yellow, green, blue, indigo, violet, we just took out red, one wavelength, but what about the rest? What about the other visible? Say, I took out red, but what about orange, yellow, blue, indigo, violet? What about the other ones on the spectrum there? It turns out that I can do a different layer of coating and a different combination, so I can start attacking other wavelengths. So if you put a single layer anti-reflective coating on, that would be great for one color, but the rest would still reflect off the lens. So I don't have any more red bouncing off. But if I add more layers to interfere with more wavelengths, I could arguably block out more of the reflections from the visible spectrum. And this is where you start hearing the term multi-layer coatings. So let's go down. And what I did was I literally took a whole host of different companies. And if you look, each and every one have the lens substrate, the base. They have this little coating, actually two coatings generally. One is for a scratch resistant coating, if you will. Another is to adhere our anti-reflective. In this case, all the yellows are my anti-reflective, and I've got 1, 2, 3, 4, 5, 6. I have multi-coats, and then a top layer. Well, it turns out that you have to put some type of a scratch resistant coating underneath everything, and the better that is, the better the outcome of the lens is. You have to put another layer on for this to adhere well, otherwise it'll peel off. And you have to do many layers of the coating in order to account for each of the different wavelengths. So if I had an anti-reflective coating that had 3 or 4 layers, I could pick 3 or 4 wavelengths out. If I had multiple layers for different colors, it's going to be more effective. So if you've ever seen certain anti-reflectives look better than others, certain of them have a better anti-reflective property than others. There's this really bright green, crazy reflection, like that's not a good AR, but my manufacturer said that's my AR, as opposed to some look virtually invisible. It's essentially all the different layers, and some have more layers and are more comprehensive and took longer to apply than others. And this is how an anti-reflective coating works. Now, you can control what colors are still reflected. So oftentimes, if you've seen some ARs are more green, and there's a reason for that we won't get into. Some like Zeiss used to have a blue or even a gold. You can control, because in some cases there's something that's still going to be residual, because there's only so many coatings and a lot of layers you can do practically. But even some, it's almost like there's nothing that comes out. And the higher the quality, the more stacks you have, generally the better the AR in terms of its efficacy, in terms of how it eliminates reflections. And that's why when you hear a multi-stack, well, what is multi-stack? Is it 3 or is it 10? Well, ask your the lab, because these are all very similar from different manufacturers, and they're all saying about the same thing. I want you to know how many different layers, how are you applied, what is the difference between a Hoya EX3 and a Crizal Sapphire versus iCoat is a private place. There's a lot of similarities, and the more you know about how this works, the more you can cut through the marketing nonsense, which is a big deal for me. Now, notice how there's more than just the anti-reflective though. And here the yellows are the anti-reflective, here the yellows are the anti-reflective. Here you see layer, proprietary, layer. These are all the different layers for different reasons, or in this case, all these different colors of the AR, but there's still stuff on top and still stuff on the bottom. So let's talk about that for a minute. Now, practical considerations. I could literally throw any AR on just about any lens, but back in the day, we only used glass. We used glass lenses, and we used inorganic compounds like silicon dioxide, and we would apply these very thin films, and they worked wonderfully. And actually, what I'll do is I'm going to do this part 1. We're going to stop here, and then I'm going to do another one so they're not so damn long.